So, good day, everyone. Let's just wait for a couple of minutes for more people to join. Okay, good day. Um, nice having you guys here again. So today we'll be talking about I'll be talking on time series and everything about time series. So let me share my screen so we can get started. Hopefully, it will not be a long one. Time series is a lot. So I hope my screen is visible. All right. If my screen is visible, you can. All right. Okay, I hope it's visible. Okay, so today we'll be talking about time series. I'm talking on time series. Everything about time series that I can talk about for this session. So um, um, as you can see, I've prepared some notebooks for us. I don't know how many we can cover today, so I'll try to cover everything. Okay, so we'll be starting from the beginning, right? So we'll be talking about time series. I know we all know what time series are, right? So we're going to build on that. We're going to start talking about random walks, about those functions that are the same called autocorrelation functions, the PACF, moving average, autoregressive. Then maybe by next session we'll talk about the Sarima model and the profits, right? So hopefully by next week that will be covered. So today we'll be talking about random walk. No, random walk is just like a process where, like, if you've seen how the stock market is, or let me just assume like something like that, right? So there's equal chance of price going up and price going down, right? So for example, like stock prices in financial markets, like there's an equal chance of a particular price going up and going down. Sometimes it might not just be random. There might be some effect. There might be some things causing those things to happen. But overall, it's kind of random, right? If you're not educated well, if you're not trained well in it, right? Um so now there's most likely a function. We're doing a lot of some kind of functions. We're talking about some functions here. And so a random walk is represented by an equation, right? Right. And the equation is the current value yt, the function of a constant c, random number et, and also the previous time step, right? The previous value. So it makes sense. Like the current stock price is most likely determined or dependent on the previous price, the some random noise, right, and a constant value, right? So and some constant value, you know, there's always this constant. There's always this constant, right? So today I'll be showing us a notebook on how to do some forecasting on these, right? I'll be explaining some of those things we're seeing in that material. If you have any questions, you can ask me. I don't know if I should be running this, so this is already wrong. Just need to explain it so it doesn't waste time. Actually. So for today, we're going to simulate a random process, right? This is a random process. So what this means is that if you look at the one on top and the one below, we can see that the C here is 0, right? So if C is zero, we can see that Y naught is zero. So what we're going to do, we're going to use NumPy to simulate a random process, and we're going to like expand on it. So we're going to like we're going to create a standard normal. So this is just like Gaussian distribution, right? Between 0 and 1. We're going to create 1,000 samples of that. Okay. Say my network is unstable, my internet is unstable, but I hope I'm still audible. So I'm going to create a random walk. Let me just run it. Let me just run it. So I can just be displaying some stuff. All right. So let me show you what steps is like, right? Steps is just from numbers between 0 and 1, right? They're just the Gaussian distribution, normal distribution. Right, so I also set the first value to 0 because we said that the constant C is 0. We're simulating a random walk, and we're saying that C is 0. This is the function we're simulating. C is 0. So I'm going to plot it out. C is 0, so we're setting 0, it equals to 0, right? And so to get the random walk itself is like summing through everything, right? So what a Combs sum does is that if you have a value 0, 1, 2, right? Combs sum is going to transform that to something like 0, 1, 3. Okay, let me say 0, 1, 2, 3. Okay, let me show us instead of narrating too much. 0, 1, 2, 3, 4, 5. Right? So if I put this in np.comsum, we are saying that it's just going to add everything and make that the value. So 0 plus 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 2 is 3, 2 plus 3 is 6, right? And 6 plus 4 is 10, 10 plus 5 is 15. So that's what chromosome does. So it's just doing a cumulative sum of everything. And that's the actual random walk. Since we're going to be summing this, so we're saying that YT is the previous value plus a random noise. So that's what this chromosome is in, giving us that series. So if I plot it out for us, so we can see what the distribution is saying is. So we can see this almost looks like how the stock market is, right? You can just see there's some randomness, and if you look at this, if you looked at your if you've looked at your material, you understand that you see that there's no seasonality. Time series, there's trend, there's seasonality, and there's one other thing. I think that is it. Yeah, white noise. So in a typical time series, you have a trend. There's a trend here, but there there is no seasonality. Seasonality as in there are some patterns that repeats themselves over some time, and there's no seasonality, and it's just random. So now we're going to talk about how we can identify a random walk, right? So a random walk is a series that first difference is stationary and uncorrelated. This means that the process moves completely unlike. Now I know you must have heard of what stationarity is, right? Stationarity. So what stationarity is, and a stationary time series is the time series that the statistical properties don't change over time. So statistical properties like mean, variance, correlation, these properties are independent of time. So if you plot the I wish I had the whiteboard, but if you plot the mean of this system, right? If you plot the mean, does it change with time? Right? Does it follow a function? If it follows a function, that means that particular series is not stationary, right? So that's that. So there's now a way in in statistics where you can test for stationarity if you can't see it at first, right? There are some tests you can use to determine the stationarity of a particular time series. Right. So to do that, there's something called the augmented decay flow test, right? And this test will help us. We're going to test. We're going to like show us if this particular thing a time series. This particular series is a stationary time series, right? And if if it's stationary, there's going to there's going to be a presence of unit roots, right? If it's not stationary. And the null hypothesis states that a unit root is present, meaning that time series is stationary. But like always, you can always reject the null hypothesis if it doesn't follow the a particular if it doesn't have a unit root in it, right? If you can reject the null hypothesis, right? So now, if you have now something that is not stationary, how can you make it stationary? To make it certain time series stationary, you can apply transformations to it. Transformations as in differencing, right? Where you just subtract YT with the previous time step, like a particular price today with a particular price yesterday, right? So that's just differencing with that's what differencing means, right? So you can always do a differencing and you can always use a log function to apply a transformation. And that transformation is going to make the series like have a standard mean variance and whatnot. So let's just do the theory, right? So we can if so for everything we're going to do today, we're going to use the stats model package. And I'm sure like the stats model package is open and you can always it comes with conda, so you don't really need to bother yourself about installing it. Right. So you can check out the documentation to API reference to just check out what's everything I'm saying. It's all here. So we're going to use the method called the AD right, on that random walk that we just created. Remember, we created a random walk process, right? And we're just trying to test, is it a random walk, right? Or is it stationary? Is it not stationary? What can we do to make it stationary? And what and things like that. But from first display, we can see that it's not stationary. Why? Because if we take the mean of this thing, we see that the mean, right? If we take the how will I put it, the time series mean or the moving mean of it, you see that the mean is changing with time, right? And we will also see that there's some trend in it, right? And we see that this is not a stationary series, right? So if you just run the test on it, we see that for it to be for it to be non-stationary, it means that this value must be a very high negative value, and this value must be less than 0.5, right? That's when you can reject the null hypothesis, right? So now if you see that it is also not is not stationary at first from this, right? So we can also plot the autocorrelation function of it, right? So what autocorrelation means is that from the name autocorrelation. So you know what correlation is, like Pearson correlation. It looks at the relationship between two variables, right? For time series, you're looking at the relationship between lagged variables of the time series. So imagine you have a time series that is recorded every hour, every minute, right? So what autocorrelation does, look at the relationship between the value at the current hour and the value at the previous hour, or the value at the 2 hours before, 3 hours before. So that's what autocorrelation does, right? It's just checking the relationship between lagged values of the time series. So we can import a function also in the stats model library called the plot is here. That helps us to visually show if it's going to help us plot the autocorrelation of a particular time series. So if we plot that, we see that now there's something that needs to happen. But if you look at it, you see that there's a correlation between each lagged values in the time series, right? So we can say that this this is a this is not a stationary this is not stationary at first, right? This is not stationary at first. So now what we need to do is to do a difference. Like I said, to get something to be stationary, you can apply transformations, right? And when you apply a transformation, it does something to it, right? What it does is that it helps stabilize the mean the variance and whatnot, like in the station in the time series, right? And so if I apply a differencing, and what the differencing is, you just subtract the previous value, the forward value from the previous value. So if I show us the random walk, let me just see if I can select to the fifth one. And if I show us the diff random walk, that's the difference one. So we see that the particular value is the difference between this and this, and this and this is this. So that's just what the difference does, right? So if after applying a transformation, you can now test, is it now going to be stationary? And if you plot that, we see that, like I said, first reject the null hypothesis. This must be a very high negative value, and this must be less than 0.5. And you can see that it follows, right? So it is now stationary. Okay, so if we plot the ACF, the autocorrelation function, now we can see that it has a significant value at lag 0, which means that this is now stationary. But let me now apply this in a real example, right? In a real world example, like Google stock prices. Right? So I'm going to use pandas, and now I'm going to import the CSV. So every data I'm using is in a folder, and so I'm now going to plot it, right? So we can see. So we can see now that if this is the closing price of Google stocks, right? From, I think this is not supposed to be, this is supposed to be January. Okay, so it's the closing price between, I've forgotten the year that this data is from, but it's the closing price of the stock from May to April of a particular year, right? So it's now, we are not going to analyze, we're not going to look at this, right? We're looking at this and we're seeing that is this particular time series stationary. From like looking at it visually, we know that this is not stationary, but we can always use the test to be sure that if it's stationary, right? So if you apply the augmented Decafulli test on it, we see that the ADF statistics is not a positive value, and it's not even a large positive value, and the p-value is much more greater than 0.5, right? So we can see that this is not stationary. So now, like I said, if you want to get, because most of, let me now see why we're bothered about stationarity. Most of the statistical models we discuss for now need stationarity to work, right? Because they need some specific parameters, right? They're working with specific parameters. And if those parameters change with time, that means you're not forecasting anything. You're just going to, it's just not going to give you accurate values, right? So that's why we want stationarity. When those statistical properties, those parameters are stable, then you can apply those forecasting methods on them, like the moving average, the autoregressive, and also the autoregressive moving average, right? The AMA. So these statistical methods, you can apply them to only stationary time series values, right? So that's why we're bothered about stationarity. So now I will apply the difference from transformation. And like I said, there's not only one transformation you can apply. There's, I think, two common ones, the differencing and the log. But we're going to stick with the differencing for now, just to not make it look, not to get ahead of ourselves. So if I now use the augmented Decafulli test, we see, like I said, this is a high negative value, and this value is much less than 0.5, right? So if I plot the ACF, now there's something that is very important here, which is that this, let me interpret this. When you see this box, it's almost about significant value, and we see that there's no lag value that is higher than the significant value except for year, which we can say is not consistent, right? So the only consistent significant value is the at lag 0, right? So we can say that this particular the difference one of this the difference series of the Google closing price stock price is now stationary, right? So, but the thing is that even after doing this, since we know that this is a random walk, right? This is a random walk, right? Like, because if you remember from when I defined the random walk for us, it's that the random walk is just first difference is stationary and uncorrelated. Since we have applied the difference method transformation, and we check the stationarity and it's stationary and it's not correlated. Now we know that this is random walk, right? So now the thing about this is that when you know that something is a random walk, right? How can you actually forecast a random walk, right? It doesn't really make sense. You can actually try, but you know that you can't successfully predict a random walk. So the thing you can do most likely is just apply some wow, 22 minutes gone. I was trying to cover a lot. So the things you can do actually is that you can apply the mean. I want to go to the moving averages, right? So you can apply the mean. So what I'm talking about is that, like I said, a random walk, the next value is most likely is random. Like it can be the possibility of it going up is the same, it has the same chance of it going down, right? So how can you predict this, right? You can always apply the mean across the whole, like what we're doing now is that we're saying our train data is from first to the 800 value, and we're saying the test is from 800 to last value, right? Because when you are doing forecasting on time series data, you can't do the random split that we did in regression. Why? Because if you know the value in the future, you're actually like cheating, right? Because if you have a task now to predict the weather for tomorrow, right? If you have a data and the weather for next tomorrow has been given to you, you most likely have a higher chance of predicting what will happen tomorrow, right? But in real world, in real life, you can't know what will happen in the future because that's what you want to predict. So that's why when we are doing the splitting in time series data, you have to do it sequentially from particular time to a particular time, then use those time ranges to predict the future. And that's what we're doing here, right? So to predict the next 200 days of the Google stock prices, I calculated the mean from the train values and I just appended everything to be the mean and I printed it out, right? So everything is just the mean, right? Which doesn't make sense because we are seeing the actual value and we're seeing how far off we are, right? For another one, we can always use the last value, the last known value to predict all the future values, and that's what we're doing here, right? For another one, you can always use something they call a drift, where we are calculating the gradient, something like a linear function, right? So you're calculating a drift and you're using that drift to something like a gradient. If we did mathematics, if you have math students or maybe statistics students here, we can always see that. We can always remember that when you have a equation of a line like y is equal to mx plus c, that m is something called the gradient. So you can just determine the gradient from all of the values you have, calculate a gradient, and use that to predict the future value using that gradient. And that's what we did here. And we can always try and plot that and see how good that is. But if you look at everything we've done, we see that we're still way off. The mean is just, and remember, this is the difference value, right? This is not the actual plot. Remember, this is the actual plot. We are predicting or we are doing the calculations on the difference value, right? If you remember. So if you now calculate the mean squared error, we see that we are way, way up by almost $465. And based on based on what you're working on, you see that can you permit this kind of error or whatever, this kind of law, this kind of error in your own use case, right? So let me jump ahead into moving average process. So now remember, we said the random walk a, a function of this, where the current value is a function of a constant random random noise and the previous y value. So for the moving average process, you see that the current value is dependent on the mean of the series. Now remember the mean of the series. So if you want to use the mean of the series, you most likely need the mean to be constant, right? You need the mean to be constant. That's why we're talking about stationarity. So imagine if you are using a mean value that is changing with time, this can get very, very complicated for you, right? So that's why we're bothered about stationarity, because if they're not stationary, you can't use the moving average process. And let me recap that this NA moving average process is a statistical method for forecasting some kind of time series problems, right? So this is not going to work for all, depending on on the on a particular value called Q, the order of no. This is not going to work for every time series, yeah, because some of them might not fall into this moving average process, right? Some might be an autoregressive process, right? So the first thing of if you are given a time series problem is most likely, do you want to know what kind of process that is, right? So if you know the kind of process it is, then you can now determine what kind of statistical method you want to use for it, right? So they are different. There's the MA, and I'm just recapping, there's the AR, there's the combination of the two called the ARMA, right? And there's the SARIMA. SARIMA, the S in front most likely is for seasonality. So if you have a data set and there's seasonality in it, you're most likely it's not going to follow the moving average process and the autoregressive process. So you can now use the SARIMA, and there's now the SARIMAX, and there's now the prophets, right? So I'll try my best to cover the prophets in the next lab, but let me run through this, right? So the moving average process is something like this: linear dependent on the mean of the series, the current error, and the past error terms. Right, the past error terms. If you can look at this, if you can see this function, um, I hope this is bold enough. But let me expand it. Okay, so it's not zooming. Okay, so let's just do it like this. So now the most important thing about the moving average is that if you know that this is a moving average process, we are going to find out if this is a moving average process, right? Now, in the process of finding out if it's a moving average, you need to find out is it the order of the moving average process, right? So now, why is the order important? Because you want to know how far back are you looking at. Remember, if you look at this equation, there's a mean, there's the error term, right? There's now a magnitude to each of the previous error terms. Now, you want to know how far back am I going to look at, so I'll know where to stop for this process, right? You can go as far back as 2, 3, 4, 5, 6, 7, 8. So this Q, how do we determine this Q, right? So that's what we're going to build on for this session, and most likely end there, or go to the autoregressive, then end there. Okay, so now what we're going to show is how I'm going to identify the order, because that queue is called an order, right? And like I said, is how far back, right? The number of past error terms are we going to consider is going to affect the present value, right? So now to do that, we're going to use pandas, the stats model, and every other thing, right? So uh, let me stop this one. This is not Jupyter. So I'm going to import a data set called widget sales. So it's for a particular store, how much widgets they sell every day of every week. think it's most likely every day. Yeah, so I'm going to import the data and I'm going to plot it. So I'm going to create a plot function, right? So it's going to take in a data frame and it's now going to plot out some things for us, right? So now, if can I plot out the DF? Let's see if it's going to work. Plot data DF. So we can see this is from almost 2 years, and we know why this is happening. So this is data we're working with, widget sales, right? And it's most likely per month or per day. I don't know. Let me look at the DF again. Let me look at the data frame again. This is daily. This is daily widget sales, right? Because you can see it encompasses a year, that is 365 days and some like 500 days. So this is, I hope I'm still audible. Hope I'm still audible. All right. Okay. So if we plot that, we can see visually that this is not going to give us a stationary, this is not going to give us stationary time series. Why? Most likely the mean is changing. There's a trend. Is it that is a trend? It goes down and it goes up. Another cool thing is that there's no seasonality. We're not seeing some kind of seasonality patterns there. When we get to the parts of seasonality, we'll definitely know, right? So, like always, as statisticians, you most likely want to test for stationarity for this particular data frame. You want to test for stationarity, this particular data frame stationary or not. So we're going to use the augmented, I don't know why I use the AD Fuller test. And like I said, if the ADF statistic is a large negative number and the p-value is smaller than 0.05, our series is stationary. Else, we must apply transformations to get it. Sorry. Otherwise, we must apply stationary to get it. Apply transformation to get it to be stationary, right? So now we can see that this is not a stationary time series at first, right? So like I said, we apply transformation. Transformation we most likely we're going to apply this series is the difference, the differencing. You can always apply the log. And so if we run the test again, we can see that it's stationary. Why? Because it's the last negative value minus 10.5, and the p-value is much smaller than 0.05. This is 7.0 times, so it's from minus 19. It's a very small value. And now, since we know that we need to okay, so we now need to check for autocorrelation, right? So when we check for autocorrelation, we can now do some, whenever we can now check, we can now know the order of the time series, right? First things first, like I said, we check for stationarity. If it's not stationary, we apply transformation. When we apply transformation, we check for stationarity again to be sure that it's stationary, because sometimes it might not be stationary. And when we are done with that, we use the autocorrelation function. Now, what the autocorrelation function does for a moving average value is that it gives us that Q, that order of that time series, right? It gives us the Q, the order, like how far back is important, right? If you remember, this mu plus noise plus the error, this like magnitude or the magnitude of the error terms, this star, yeah, is how much are we focusing? Almost like weight in linear regression. So now we're looking for how far back is important for the current value. Now, if you look at this plot, the autocorrelation, like I said, it gives us correlation of lag values. And if you plot it, we see that the zero, this means that it's high. That means there's a correlation, right? At the zero, you remember, correlation of something with itself is one. Always. A variable with correlation of a variable with itself is always one. And at lag zero, when you say lag zero means that there's no lag at all. And when there's no lag, you're checking the correlation with of the value itself, and you most likely have one, right? So now we apply at lag one. That means one step forward, is it correlating? You see that there's no correlation, 0.6. You go another step forward, that's at lag two. Is there a correlation? We see that there's a significant correlation, 0 point whatever. But any value that is within this box, right? Any value that's within this box means that it's not significant, it's insignificant to us. So we see that they are significant coefficients up until lag two, right? Then they are probably abruptly become insignificant as they remain in the shaded portion. So this means we have a stationary moving average process of order two. We can use the second order moving average model or MA2 model to forecast this particular time series. That's why I always wanted to come here, because it's going to make sense when we come here, right? So since we've determined the order of the time series, we can now go into forecasting, right? So now, like I said, we are going to use 90% of the data to train, and we're going to test on the remaining, right? And remember also, if we use 90%, it's 490 we get 490 plus 50, 500, because we have a length of 500. But also remember that when you apply the difference, that the first value is lost. Why? Because this first value now is not going to be subtracted with anything, right? You subtract this with this with this. So let me point it out, this with this. But this zeroth value is going to be subtracted with by, let me say, infinity. And at the end, then we have a value that is dashed, and for the first value. So that's why we lose a data point when you apply the difference transformation. I hope that makes sense. I hope that makes sense. So now if we plot
Sir, please,
out,
can you explain that part again?
oh, okay, all right. Um, uh, okay, so where's the difference in parts? Okay, all right. So let me see if I can print this out. Oh, it's the data frame. It's the data frame. Let's convert it to a data frame. Okay, I would love to use a graphic, but all right. So let me look for a particular book. I most likely should have brought the graphic to us, but let me show you the reference book I'm using so you can always look at it so you can see for reference. Yes, it's difference. Okay, okay. It's not here. All right. Yeah, this is the graphic. I hope you can see my left screen well, right? So now this is your original time series data, right? And so what you're doing is that you're subtracting y1 with y0 when you difference, like when you're applying the first order difference, right? But the output you get is the first value is going to be dash. Why? Because there's nothing to use to subtract it. That value is most likely going to be used to subtract the first one ahead of it. So that's what is now going to give us, that's not going to be our first value, because remember, there's nothing behind the first value of a time series. Right? So you're always going to lose that, because that one is going to be used to difference the second value and get your first value in the difference time series. Do you understand now?
Yes, sir.
All right. Thank you. So so if you want to know time series, there's no better book to use than this. So it gives you everything you need to know time series. So I recommend as a study material, study guide for you. Okay, so what's this? All right, let me continue. And so we're going to plot out the previous value, that means the normal time series and its difference. If you look at it, you see that there's no trend. The mean is most likely the same, right? And we see that um, there are still some sharp bend, most likely because of the noise, right? So now we're going to apply forecasting. We're going to do the actual forecasting process with the moving average model. Like I said, we're going to be looking at, I don't know if we'll be able to do that, it's very tough for 2-1. But we're going to, the moving average, the autoregressive, the ARMA, they all follow this process. Like you want to get the order, right? What's the order of it? For the moving average is Q, for autoregressive is P, for ARMA, because it's a combination of the both of them, because there might be a series that is not um, moving average and is not autoregressive. So it's a combination of both of them. So you have to find P and Q. So that's that. But now, so if you want to, let me just talk about this. So if you want to do forecasting using for the moving average model, we're going to borrow a model, the Cymax model, right? And like I told you, it's a complex model that allows for seasonal effects, autoregressive process, non-stationary time series, moving average processing, and exogenous variables, right? Exogenous variables as in external variables. Because if you look at this time series that we've been working with, compared to a linear regression, when you have something like bedroom size, number of bedroom, number of um, toilets, like in the house price or in a classification task, we see that there's just one feature, and there's just one feature, and that feature is the target, right? But in some cases, there might be some other features that determine this particular widget series, and you can add them to the forecasting, right? And you can use a Cymax model for that, or you can use a moving MA, the moving average model for that. You can use Prophet too. I'll show you that in the next session. I most likely have to skip to that. So Cymax is also able to do moving average processes, right? So we're going to define a function, right? And that function is going to take in a data frame, the training size, the horizon. So what the horizon means is that horizon, like the name suggests, is most likely how many data points are we predicting ahead. Like I said, we split it 90%, 90%. So the horizon is going to be 50, right? Our horizon is 50. Our train length is 449. Yeah. And so the window is 2 because our Q is 2, right? The window is 2. The method we're going to use, we're going to define 3 methods, right? So we can look at we're going to look at the metric to see which one is the moving average better, right? Is even good enough? Because we're going to use the metric mean absolute error as mean squared error, one of them to evaluate our performance, right? So these are the arguments for the method, right? And we're going to determine the total length just by adding the train length and the horizon. That's simple. I'm going to use the mean, right? We're going to use the method called mean, right? To just calculate the mean for each, because if you look at this, if our window is 2, the train length is 800, or let's say 449, the total length is 500 or whatnot. So it's going to look at two windows, calculate the mean, right? From then to the second window and 2 windows ahead. If let me just run it. So, but I'll most likely provide this code for us too. I know we're all Python guys here, we're all Python gurus here. So we know what this method is going to give us. So if I convert it to a list, so we see that what that 2 does is it's like a step function. It's going to from 0 plus 2 plus 2 plus 2 up until the last value, as always, right? So that's what we're going to do. We're going to calculate those steps, then calculate the mean, then put that as a prediction. Also for the last value, we're going to do that and pick the last value. So, but for the moving average method, right, we're going to now, I think I need to show the Sarimax model. The Sarimax model takes in some arguments, right? Yes, right. So this other method, so this other parameter, not method, this other parameter, right? It's it's there's a pattern to it, right? The order P, D, and Q. AR parameters, differences, and MA parameters. So the first parameter is for autoregressive, um, a autoregressive model, or sorry, autoregressive process. D is for differencing. We'll get to that uh, most likely. And Q is for a moving average process. And now, like I said, you can select one of that, right? Or you can use a combination of that. So since we are bothered with only the moving average process, we're going to put this as 0, P is 0, D is 0, Q is going to be 2, right? Because we determine the order of the moving average process for this time series. That this time series is a moving average process of order 2 or a second order moving average process, right? So, and because of that, that's why this order is 0, 0, 2, right? So that means we are not bothered about the moving average. We're not bothered about the autoregressive parameter or differencing, right? When we get to that, we'll see how to work with that, right? So, so if we select a method, the moving average, right, it's not going to use the model, just like how we did in sklearn. We create the model with the class, we fit the model, and we make prediction, right? We now append into a list. We're using a list, right? We're going to use that list. We're going to use that list to append to the data frame. Right, so we have created the function. Now we're calling the function, right? We're specifying the prediction data frame is test.copy. The train length is the length of the training data. The horizon length of the test data, like I said, is how many data points ahead are we predicting on. The window is 2 because we determine the order, right? So we're going to call predmean, prediction last value, and prediction moving average, right? While we're changing the method we're using, mean, last, and moving average. We get the list, we append that list back into our data frame, and we call data frame.head. So we see that it has done the predictions for us. It used the mean, the last values, and also the moving average model. So now what we're going to do is we're going to plot that to see how close we are with the difference data sets, right? Remember, we're still working with the difference data sets. This is not the actual data set. We're still going to do the undifferencing transformation. So we can actually see it in the normal data set. So if we plot that, we see that how close they are with the mean, the black is the moving average, right? And the last values. The last values is most likely just a lag version of the current value. So just a lag version. So now we're going to evaluate our model using the mean squared error, right? So we're going to import mean squared error from sklearn. We're going to call the mean squared error on the predicted and the true value and the predicted value to calculate the mean squared error, right? So we're printing out the mean squared error of the mean method, of the last method, and the moving average model. And if we plot it with a histogram or with a bar chart, we're using a bar chart here, so you can visually see. We see that the moving average had the smallest and the lowest MSE, followed by the mean and the last value, right? So now remember, we're working with a difference time series. We now need to undifference it. I know this is going to get complicated here. Hope it's not going to get complicated, but what we're going to do is that, remember, the y at a particular point is y1 minus the y previous. Okay, let's say the difference yt is the original yt minus 1, right? The previous one. So if we want to get it back, we're just going to add that one back and do a cumulative sum. Now let me see if I can explain. So remember, this is where we're predicting from 450, right? This is the value at 450. So these are our y naught, right? So this is our y naught, and this is the cumulative sum of that difference prediction. Cumulative sum. So what it's doing is that I think you need to go back to this code and just look at what I'm doing. But let me use this equation here. We are saying that y1, the original y1 is y0 plus the difference one, because we're just going to remove that difference out of it back. Hope you can see with this particular formula up here, right? So you get your y1 back, you add the original first value into the difference value, and it's going to cancel out the difference and give you a y1 out back. So we're doing that for the whole series, right? And that's why we're using the cum sum. And out the moving average, what do you call it? The moving average process, or sorry, the moving average model performance with the actual, sorry, the predicted on the true value, we can see how far off we are visually, right? And so if you use the mean absolute error to check how far off we are, you see that the mean absolute error is about 2.32. And the data sets we're working with came in thousands of dollars, right? This is $50.496 thousand. Sorry, so that's $50,496. Sorry, yeah, that's it. So the dot here means that it was divided by 1,000. Okay, hope I'm still audible. Okay, lost my connection again. So if you're talking to your boss or to a CEO, how can you tell him this metric? Is that our predictions are on average $2,320 off or above or below the actual value. So if you are talking to a CEO, he will most likely tell you this isn't good enough. You have to try a better method. So in next session, we'll brush through the remaining and talk about the profit model, which is the last model, or the de facto model in time series. Right. So if there are any questions, please you can ask me. Am I audible? I didn't know questions. You can type it in the chat too. All right. So if there are no questions, like I said, I showed the data frame, the book that is most likely encouraged for you to practice on. I'll share the notebook I used today with everyone to just get their hands dirty. And yeah, I'll see you by next week for the other session if you have no questions.